on this sample problem number 3 on work, let me read first the problem. A box of 100 pounds of sand is being pulled up at a uniform rate at a distance of 50 feet over 1 minute. The sand is leaking from the box at a rate of 1 pound per second. The box itself weighs 5 pounds and is pulled up by a rope weighing 0.2 pound per foot. Now, there are 3 questions for this problem. How much work is done lifting just the rope? You're exerting force in lifting the rope because your rope is not weightless. So it has a weight of 0.2 pounds per foot length. Okay, so how much work is done in lifting this rope? Then how much work is done in lifting just the box and the sand? So the problem actually isolates the items that you are pulling, though they are all pulled up together. So in letter B, you are asked to determine the work in lifting just the box and the sand that it contains. Whatever is the remaining amount, since this sand is leaking in your box at a rate of 1 pound, or from your box at a rate of 1 pound per second. Then last requirement is what is the total amount of work performed. So in this case, now you are to consider the work done in lifting the rope and the work done in lifting just the box and the sand. So you are to take the sum of the two. Okay, now we start with letter A. If you recall our first 2 sample problems, you're also lifting a rope up to the face of the cliff. So this one is similar in principle to that one. So we start by forming the force function for the rope, and as such you can see here that it has a subscript of R. You can see here the subscript R, meaning this is the force needed to lift your rope, and it is a function of X being the displaced length of the rope, since you know, as you pulled up the rope, you're only exerting a force on the remaining part of the rope that is not yet pulled up, or that was not yet pulled up. So what is this force that you are exerting on the rope as a function of the displacement of the said rope? Now, as in the previous example, let X denote the amount of rope in feet that is pulled in. Okay, the amount of rope that is pulled in already. So if it is X, then the remaining amount is 50 minus X. The remaining amount that needs to be pulled in is 50 minus X. Okay, this is the length that is remaining. And what is the mass for each foot of that particular rope? You can see it in here. It's 0.02 pounds. So you're multiplying this length with the mass per unit length, giving you the mass already. Now, since this is English, you have the unit pound. This is an English unit. We'll just assume that your G and your G sub C for this particular problem are just the same. So your mass in pounds is also your force in pound force. So that is why you just simply multiply the mass here with the length of the rope that is yet unpulled up. So if X is the pulled up length, then the unpulled length is 50 minus X. So if you're going to do expansion, in this case, you will have 10 and you will have minus 0.2x for the force. And we know that work is equal to the force times the displacement. In this case, this is your force needed to lift the weight of the rope. So this is the force for lifting the rope, and this is your displacement. The dx is your displacement. The limit of your integration is from 0 to 50 because it says here that you are going to pull up the rope at a distance of 50 feet. So it's from 0 to 50. And I think you know how to do your integral calculus for this one, even if you don't have your calculator, because you will simply use power rule here. And then after that, to your answer, you just substitute 50 because for the lower limit, which is 0, of course, your answer would all be 0, with x being 0. So for letter A, in terms of the work done in just lifting the rope alone, it would be 200 foot per pound force. Foot pound force, not per pound force, but foot pound force. Okay? Any questions so far?
None, miss.
None. Mr. Librando, you're saying that you cannot hear me? Miss Indica Bation. Is there something wrong with my audio? Can you hear? Everybody can hear my voice?
Okay na, miss.
But maybe that was just a few minutes. Okay, so no question with letter A. Now we go to B. Anyway, this is just a short sample problem, just making use of the remaining time. So we go to the next slide. Now, this time you are to determine the work in lifting the box with the sand. However, the catch here, class, is this. The sand inside the box is leaking. So there must be a hole in that box because the sand inside it is leaking. So meaning, during the time that you are pulling up the box with the sand, the weight of the sand inside it is decreasing. So the sand is leaving at a rate of, or leaking in your box at a rate of 1 pound per second. So as the vertical trip is to take 1 minute, which is equivalent to 60 seconds, then we get 60 pounds of sand from the box. Meaning when your box already reaches the height of 50 feet, by that time, the remaining amount of sand in your box will just be 100 minus 60. Because this 60 pounds would have left your box because from this rate in which your sand is leaving the box, you will multiply 1 pound per second to 60 seconds. So then the total mass that left for a minute is already 60 pounds. So then the remaining amount is 40. Okay? Now again, letting x represent the height of the box, we have 2 points on the line that describes the weight of the sand inside the box. Now let me explain this one to you. You have conditions in letter B. I'll just write it in here. For letter B, you have conditions. So the first condition is this. I'll place here condition 1. That at the height 0, when the displacement is 0, of course, your sand has not yet, or no sand has yet left your box because it was not yet lifted. So by this time, the mass of the sand inside the box is still 100 pounds because it was not yet lifted. But when x is already 50, when your x is already 50, we know that the remaining sand inside the box would be 100 minus 60. And that would be 40 pounds. Because we know already that after a minute, for the 50 feet distance covered, you have already lost 60 pounds of sand inside your box. Now, what will you do with this set of values that you have? Displacement with the mass of the sand remaining in the box. Now, you are to look for an equation. You're going to look for the equation of the force in terms of x, the force that you need in lifting up the box with the sand in it, however is the condition may be, whether it's x equal to 0, x equal to 10, x equal to 25, or x equal to 50. Okay, so you should have a general equation relating displacement and the mass of the sand in the box at that particular displacement of the box. So let's say we'll represent the force needed for the sand and the box together. So I'll place here the subscript SB. So you don't know this equation. It should be a function of x. Now, if you recall, in the equation of a line, you have y equal to mx plus b. You know this as the general equation of the line. And in here, this y is comparable to f. and this x is comparable to your displacement x as well. Now we will need the m, the slope of that particular line. So how do we get the slope of this particular line? Just like, I'll place it here, just like in your analytic geometry, you have y2 minus y1, m2, x2 minus x1. Okay, you know this is the formula for the slope. So we will find for the slope of the line. But this line is an equation that relates the force in lifting the box with the sun as a function of displacement. So let me just rewrite again. So you have here x2 minus x1. So in this case, you will have, for the numerator, you will have this m, 100 minus 40. And for the x, you will have, if you have subtracted class in this manner, 100 minus 40, when you subtract here, it should be 0 minus 50. Not that you have subtracted, your subtraction here is 100 minus 40, and when you do the subtraction in the denominator, that would be 50 minus 0. That should not be the case. Kinahanglan kung ano ang order sa pag-subtract mo diri, amo man ang order sa pag-subtract mo diri sa idalog. Okay? Now, so we'll have now this one equal to 60 over negative 50. And this is equal to 1.2, and that should be negative because you have negative here. So for your formula now, you will have F equal to negative 1.2x, plus B. Now, question. I'd like to change the color of my pen. Question, what is this B? This one, this B. So remember that when your displacement is yet 0, you know that the mass of the sand inside the box is 100. So it follows that this F would also be 100 when x is equal to 0. So 0 here, if you substitute 0 here, and you substitute 100 here, it follows that B is equal to 100. So it follows that, so I'll use Shakitanon, that your force equation now for the sand and the box is negative 1.2x plus 100. So again, I will repeat why you put here 100 in B. It's because when your displacement x is 0, you could see this condition here, that when your displacement x is 0, the mass of the sand inside the box is 100. So you place here the force to be 100. You just substitute x equal to 0 here and you place here 100. So anything multiplied to 0 is 0, so your B is 100. However, this is not yet done, because if you notice, my subscript here, class, is sand with the box. So the equation that I have written here so far is just all about the sand. Remember, this negative 1.2 is taken on the set of values here of the mass and the displacement of the sand. And this 100 is also for the sand. Now, you have to take note that, where is it? That the box alone, the box itself, it says here, the box itself weighs 5 pounds. So you have to consider it irregardless of where the displacement is, whether it's 0, it's 10, it's 20, it's 25, the mass of your box is constant at 5 pounds. So what you do, you're going to add it here in the constant. So this is now your final equation. Your final equation for the force relating, the force needed to lift the sand with the box is negative 1.2 x plus 105. This is the final force equation. And that's the thing that you see here being placed for the force. The displacement is still dx, and you still have the limit 0 to 2. Now, if you're going to do the maths here, you perform the integration, you will have 3,750 foot-pound force. Now, before I proceed to the last, because the last would simply be taking our answers in A and B, do you have any question with letter B? Any questions? Is this clear? So you found the slope of the line relating the force to the mass and the displacement to the conditions that I have written in here. You got the y-intercept of this form of the line equation by substituting the 0x here to the x here and then substituting 100 in here. So you will have a b equal, of course, to 100. That's it. But you need to modify it because if you just stick to the equation which is negative 1.2x plus 100, you did not consider the weight of the box itself. And the weight of the box itself, class, is fixed. It's not changing whether your elevation is 0 or your elevation is 50 or mid-weight. It's still 5. So that is why it's added here on the constant, which is 100. So this 100 becomes now 105. And then we use the equation for the force needed to lift the sand, the leaking sand in your box with the box. This formula for work. For letter C, all you have to do is take the sum of the two works. So what is the total work performed? The work in lifting the rope plus the work in lifting the sand, the box with the leaking sand, that is. So you just add 250, our answer in A, to 3,700 here for letter B. That would be 4,000. Another way of doing letter C is the force equation that you have for letter A and B. So this is the force equation for the rope, the 10 minus 0.2x. You add to that the force equation for the box with the leaking sand. And then perform the integration on the simplified equation, which is negative 1.4x plus 115. Still, your limits isn't changed. It's still 0 to 50. You will still be getting the same answer. Any question? So no question. Okay, so for Thursday, there are no questions here. I clear my markings.